Hello, today we'll be continuing with section 1.4. Okay, so let's talk about polynomials and what are polynomials. Okay, now many of you know that a number like 5 or an expression like 5x to the 6 plus 7x, that's a polynomial, right? We call this sixth degree polynomial. If I have 3x squared plus 10x plus, say, 6, right? That's also a polynomial, that's a quadratic. But if I have, let's say, 5x plus 1, right? Y equals mx plus b, this is the equation of a line. That is also a polynomial. This is a first degree polynomial. And a number like 10 or a number like pi, those are also polynomials. These are like 0 degree polynomials, right? Because it's like 10x to the 0 or pi x to the 0, or x to the 0 is 1. So all of these are polynomials. We can solve polynomials a bunch of ways. Let's look at this first one. This one says solve a polynomial by factoring. So I'm going to write this as, let me just copy it here. Or actually, yeah, let me copy this here. 3x to the 4th minus 6x cubed. And then let me subtract 24x squared from both sides. So I get this whole thing equal to 0. And then I want to factor out an x squared. So if I factor out an x squared from the first term, I'm left with a 3x squared in the first term, and then I'm left with a 6, and then I pulled out 2 x's, so there's 3 x's here, I'm left with 1x, and then I'm left with a 24x, just 24, sorry, oops, equals 0. And then I see to myself, wait a minute, I could have also factored out a 3, right? Is 3 the highest term, the highest common thing I can factor out here? Yeah, so let me pull out a 3. So then and you could have done this in one step too. X squared minus, whoops, if I pull out a 3 from here, I'm left with 2x and minus 8 equals 0. Okay, and then I can factor this trinomial, right, this polynomial of 3 terms. Factors of negative 8 added to give me negative 2 are going to be x minus 4, x plus 2, right? So that gives me minus 2x and minus 8, and I have a 3x squared here. So now each of these is set equal to 0. Okay, so that tells me that x equals 0, and x can equal positive 4, and x can equal negative 2. Okay, and you can check this, take any one of these numbers and plug it in to this original expression here, and you'll see that they should equal each other. The right side should equal the left side. Okay, now let's look at rational functions. A rational function is a quotient of polynomials. So a rational function, let's call it r of x, is a quotient of two polynomials, p of x and q of x. Both p and q are polynomials, and the denominator q of x cannot equal 0. Okay, that is a rational function. Graphs of rational functions have asymptotes. What are asymptotes? They are lines. The graph approaches. Okay, so they can be vertical or horizontal. So lines that the graph approaches, or the function approaches, but doesn't reach. Okay, so here's the question. Graph 3x plus 2 over x minus 2 on the calculator. And what are the asymptotes? So let me pull up my calculator here, and y equals 3x plus 2 over x minus 2. Okay, let's put this in parentheses. 3x plus 2, whoops, I can do this, over x minus 2. And then let's go back and let's go to zoom 6. And you can see we have some asymptotes going on here. We have a vertical asymptote and a horizontal asymptote. Okay, so if I hit trace, right, you just keep going down and down, and my x value is 1.4, 1.7, 1.9, and then it jumps. Did you see that? So from 1.9, the y value is very small, negative 91, but then when it jumps to above 2, it goes up to 65. So it's like goes down here and then it does that jump. And if you try to trace at 2, that value is undefined. Why? Because if we put 2 in the denominator, we'll get, if we put 2 in for x, we'll get 0 in the denominator. Okay? So it seems like x cannot equal 2. So x equals 2 is a vertical asymptote. Okay. And I denote that as VA. And then let's look at this one here. And it seems y equals, let's see, let's trace this. So at 2.3, 2.5, there's the graph, or there's the cursor. Okay. What is that value approaching? Seems to me it's getting closer and closer to 3, right? Let's plug in, let's trace y equals, I don't know, 20. You might not do this because it's out of range. Yeah, it's out of range. So let's fix the window. Window, make it go from negative 20 to positive 20. Okay. And if you hit trace, or I'm sorry, if you hit, yeah, trace and then try, let's say 19, see it gets very close to 3. Okay. And if you zoom out some more, okay, so let's set our x min at negative 100, x max to positive 100. Let this graph it, and we hit trace. Let's try 99, right, 3.08. So it seems that the horizontal asymptote is approaching 3. Okay, so y equals 3 is the horizontal asymptote. Okay, I'll just abbreviate it here. Okay, horizontal asymptote. What is the domain? Now here's a practice problem. What is the domain of f of x equals 18 over this function? So think to yourself, domain, right? Possible x values. So what x values will make this whole function undefined? Well, I cannot have a 0 in the denominator. So x plus 2, x minus 4 cannot equal 0. That means x plus 2 cannot equal 0. X minus 4, either one of those cannot equal 0. That means x cannot equal negative 2 and x cannot equal 4. So the domain is all numbers except for negative 2 and 4. So we start at negative infinity, and then the number line goes all the way up to 2. We're not including 2, so it's a parentheses. Union. All numbers between 2 and 4 are valid, but we're excluding 4, and then 4 to infinity. Okay, this is interval notation for the domain. Okay. Alright, and then it says, oh, I'm running out of space here. An exponential function is of the form y equals b to the x. Okay. What is b is a number? Oh dear. Scroll down a little bit. And that says y. Y equals b to the x. B is a number. Okay, that's our base. X is the exponent. Okay, So that's the variable. That's why we call this exponential functions, because your variable is in the exponent. Okay. The blank of the exponential function is the logarithmic function. So the inverse. Okay. The inverse of the exponential function is the logarithmic function. Okay, they cancel each other out, or you can think they do opposite things. Okay, write the domain of the following functions in interval notation. Okay, so 2 to the x. What does 2 to the x look like? Or what does any exponential function look like? Okay, so let's get our calculator, and you can see if you now how do you plot exponential functions? You have to do 2 up caret x, okay? And then let's go ahead and do zoom 6. And you'll see the function looks like that. That value right there, when x is 0, y is 1. Okay? When x is 0, y is 1. So that's going to hold true for these basic exponential functions. Okay? So let's look at the domain. Is there any number for which this exponential function is undefined? The answer is no. Exponential functions are defined for all values of x. So the domain goes from negative infinity to positive infinity. Okay? And the function looks like this. Okay? And that point right there is x is 0, y is 1. Okay? Even if your x is negative, like negative 1,000, that's going to be way out here. It'll be very close, the y value will be very close to 0, but it does exist. Okay? Alright, let's look at logarithmic functions. So now we know that 2 to the x, so 2 is our base. Right. If I wanted to convert this to a logarithmic function, y equals 2 to the x, then you would convert it like this. Log, what's my base? Base 2 of y equals x. That's how you convert it, right? We'll deal more with logarithmic and exponential functions later. Okay. Let's find the domain of this function, log base 2 of x. So exponentials and logarithmic functions are inverses of each other. That means they are reflected about what? They're reflected about the line y equals x. Okay? And they're inverses, which means the x's and the y's switch. Okay? So this point is 0, 1, oh, sorry. This point is 1, 0. Let me just adjust this graph a little bit. Oops. Here. And this point is 1, 0. Before here, this point was 0, 1. Okay? And a logarithmic function is going to look like this. Okay? So that's log base 2 of x. And this red graph here is 2 to the x. Okay? And they're inverses of each other. So now you can see what is the domain of the logarithmic function. Well, can you have the log of a negative number? Is my graph defined for negative x's? You can see that it's not, right? So the domain is 0 to infinity. And let me just extend this example here. And let's look at the range as well. The range for exponential functions, you can see the y values for this red graph here for 2 to the x are all positive. So the range is this, 0 to infinity. What is the range for the logarithmic function? Well, you can see it can take any value. Y can be positive or y can be negative. So y is negative infinity to positive infinity. So the domain of the exponential function is the range of the logarithmic function, and the range of the exponential function is the domain of the logarithmic function. Okay, that is going to hold true for functions that are inverses of each other. Okay, let's look at e to the x. Now, what is e? E is a number 2.7, what is it, 2.728, something like that. Okay, it just goes on. It's like pi. It's an irrational number like pi. Okay, so we know what 2 to the x looks like. Oops, what just happened? Something just happened. Okay, hopefully kept all of that there. Good. Okay, so it's there. So 2 to the x. 2 to the x we know looks like this. Okay. What does 3 to the x look like? 3 to the x is even steeper. Right? 2 to the x is saying like your money doubles over a certain period of time. 3 to the x is saying like your money triples. E is between 2 and 3. So e to the x looks something like this. Okay? And all of them cross over, or all of them hit the y-axis at this point, 0, 1. Okay? What is the domain of e to the x? The same as 2 to the x, negative infinity to positive infinity. What is natural log of x? Natural log of x is log, so this is ln, logarithm naturel, okay? We call it natural log. This is log with the base of e, okay? So e to the x and natural log of x are inverses of each other. Log base e of x. Log base e of x is the inverse of e to the x, so it looks like this, okay? And again, this point here, so that point goes to that, and this point here is 1, 0. Okay? And the domain of natural log of x is the same as the other logarithmic function, goes from 0 to infinity. Okay? So if you're ever confused about domain and range, what you want to do is graph it on the calculator and check the domain and range. Oh, let me show you how to plot e to the x. So instead of 2 to the x, you'll see the e button. If you go to second, then ln, you'll see e right there, and that's e to the x, okay? And natural log is this button right here, ln x, okay? So be very careful to use this e above the natural log, not the e that's above the division sign. Okay, that e above the division sign is the actual number 2.72 whatever, okay? So let me show you that. Let's see if you do that. 2.71828. Okay. And then we graphed e to the x and natural log of x. So natural log of x will be dark ink. Let's do zoom 6, and you can see there's e to the x, there's ln x. Okay? Alright. Another kind of functions that we're going to be looking at is piecewise functions. They're given in parts. The most famous piecewise function is the absolute value function. Okay, so what is the absolute value function? Absolute value of x. If x is positive, then the absolute value of x is that number itself, right? But if x is negative, then the absolute value is, or then absolute value of x is, or the function becomes negative x. Okay, so that's why we call it a piecewise function, because it's different pieces depending upon which part of the domain you are on. Okay, so let's graph that. So if x is greater than or equal to 0, the graph looks like y equals x, right? So you can say y equals x. So y equals x looks like this. And if x is negative, then y equals negative x. We know negative x looks like this. Okay? So no matter what the x value is, the y value will always be positive. And that's what absolute value is, right? Makes all numbers positive. What is absolute value exactly? It is actually the distance from 0. So if the absolute value of -5 is 5, which means it's 5 units away from 0 on the number line. Okay. Here's another example of a piecewise function. This is a piecewise nonlinear function. You can use your calculator to graph these, and you can read this graphing calculator exploration to graph these. Okay. Some of these you should be able to do by hand. You know what the graph of 2x plus 3 looks like. You know what 6 minus x looks like. X minus 4 quantity squared. We know it's a parabola, right? We can figure out the vertex and the x and y intercept. So you should be able to do it by hand, although I might not require it for you to do that. Alright, now let's look at the composition of functions. Okay, so if f of x equals x to the 7th and g of x equals x cubed minus 2 to the x, what is f of g of x? So that means I want f of, let me plug g of x into here. So every time you see an x, you're going to plug in g of x. So think about this. What is f of 7? Well, maybe that's a bad number. Let's say f of 9. Right? That's 9 to the 7th. What is f of 3? 3 to the 7th. What is f of star? Right? Star to the 7th. Every time you see an x, you plug in whatever is inside this parentheses. So g of x is inside the parentheses. G of x is x cubed minus 2 to the x. So I'm going to take this and plug it in for the x part in f of x. So that's x cubed minus 2x raised to the 7th. Okay? And I don't want you to FOIL that out 7 times. No, just leave it like that. Okay? F of x, so that means that's f of x to the 7th. Okay, so you're taking a function and plugging it into itself. That's x to the 7th raised to the 7th, right? A power raised to another power, we know we multiply. That becomes x to the 49th. Okay. And g of f of x. Okay, so that is g of, what is f of x? X to the 7th. That means every time I see an x in my g function, I'm going to plug in x to the 7th. So it's x cubed, so instead of x cubed, it'll be x to the 7th cubed minus 2x. But instead of x, I have x to the 7th. And then 7 times 3 is 21 minus 2x to the 7th. Okay. And you can leave it like that. We can do a composition of functions and apply it to a concept known as the difference quotient. Okay, so we're going to see this in calculus later. F of x plus h minus f of x all over h is known as the difference quotient. So let's do this in pieces. Okay, so first let's find f of x plus h. So every time you see an x, you're going to plug in x plus h. X plus h squared minus 4 x plus h plus 1. Okay. Okay. I'm sorry to pause the video for a minute. Somebody just came into my office. So let me see, where was I? X plus h squared minus, okay. So now I can FOIL this out. X squared, so you know the procedure or the algorithm for FOILing, you square the first thing, then you multiply these two together and double it. So that's 2xh, and then you square the last term, which is h squared. Let's distribute that 4 minus 4x minus 4h, okay, and then plus 1. And then can I combine any terms here? No, that is it. Okay, so now I need to, f of x I know is here, right? X squared minus 4x plus 1. So now I can put all of this together. So let me change f of x plus h minus f of x over h. So f of x plus h we have up here. X squared plus 2xh plus h squared minus 4x minus 4h plus 1. And then minus, so that's the f of x plus h part. minus f of x. What is f of x? X squared minus 4x plus 1. Now be careful, we're subtracting all of f of x, so you have to put that in parentheses. All divided by h. Okay. And let me scroll down here a little bit. So now, let me parcel this out. So this part is f of x plus h. Okay, minus this part is f of x. Okay. Now we need to combine like terms and distribute. So let me distribute that. Let me write this out. X squared plus 2x h plus h squared minus 4x minus 4h plus 1 minus x squared plus 4x minus 1. Okay, so I distributed that negative, and then all divided by h. Now things will start, we can start combining terms. So x squared minus x squared is gone, minus 4x plus 4x is gone, plus 1 minus 1 is gone. So you'll notice that everything that's left over has an h in it. 2xh plus h squared minus 4h all divided by h. Okay, and then I can factor out an h from the numerator. Oops. I can factor out an h from the numerator. Oh, something just happened. Shoot. Okay, it's all over h. Let me pull out an h. Then I get 2x plus h minus 4 over h. Okay, and then the h's cancel out, and my final answer I'm left with is 2x plus h minus 4. Okay, so that is the difference quotient for this function f of x equals x squared minus 4x plus 1. Later when we get into chapter 2, we'll actually do something with this. Alright, we'll take the limit of this and call that the derivative, and yeah, it'll be fun. So I love doing difference quotient stuff. Notice your answer at the end will have an h in here, okay? And that's what's supposed to happen. You're going to have an h in your answer for the difference quotient, okay? So these are some active learning problems. You guys can work on these for practice, and then also work on the homework. If you have any questions, please get in touch with me. I want to make sure everybody's following along, okay? Thank you for watching.